Thank you for the introduction. Last minute, I actually changed my title talk, and now it's going to be Emissions Control with Precious Metals, the more expensive the better, after the recommendation of both my advisor and one of the waiters looking at my poster yesterday that my title wasn't sexy enough. So today I'd like to share with you some of the work we've been doing in our group to understand if you really want to control methane emissions or emissions in general, do you really need to use such large quantities of precious metals? So the small molecule we'll be talking about today and that we've talked about the last couple of days is methane in the form of natural gas. As a fuel source, we're increasingly considering how methane will fit into this picture for a couple of different factors. Number one, as we increase our technologies to both extract and find these reserves of natural gas, we think that natural gas is going to have to play this larger role. There's thousands of billions of cubic feet of this resource throughout the world, and a very large fraction of this resides in the United States. Along with being a highly available fuel, it's a very versatile fuel in its applications today. So we clearly use it to power our homes, and increasingly we're using it in the automotive sector as well to power our vehicles, and we saw some of that today as well. And while natural gas surely isn't the final ultimate solution to sustainable energy, we have to realize that as we transition off of other fossil fuels, it is a cleaner alternative to the tune of producing half as much CO2 per energy, as well as other more limited species such as SOx and NOx. Natural gas does have these advantages, which is why we're interested in working with it. However, natural gas does have one large, well, maybe many, but at least one large downfall, which is that it's a terrible greenhouse gas. So we always hear about CO2 in terms of how much greenhouse gas is being produced, but the fact is that on a per greenhouse gas warming basis, methane is 20 to 70 times as bad than CO2 to release one molecule into the environment. So the goal of this picturesque natural gas-powered vehicle is that you take in methane, or natural gas, and you only produce CO2 and water via clean combustion, and you don't release any unburnt methane into the environment. And this idea is around on all sorts of vehicles in the sense of emissions control. So whether you have a car or a truck, you're going to be porting very large quantities of these rare and precious noble metals underneath your vehicle. The problem is that for example, catalyzing the reaction of methane into CO2 and water is incredibly challenging, which is why we need to use very large quantities of these rare and precious noble metals, such as platinum and palladium, which is what I'll be focusing on today. So if we want to design materials that are as economical as possible, there's two main design considerations that we want to take in mind. And that is, number one, we want to create highly active materials. This means we can do these reactions at low temperatures, with very low amounts of catalyst, and then we also want these materials to be able to be durable. So we want our catalytic converters to last long periods of time. So clearly people have been studying limiting emissions for a very long time. Yet surprisingly, when I started my PhD 2 years ago, I couldn't quite understand when you want to make an emissions control catalyst and you have platinum and palladium, do you want to combine them? Do you want to use one or the other to have the best emissions control material? And that has to do with conflicting reports in the literature. So, for example, in 2006, they found that by combining these precious metals, platinum and palladium, you get a better emissions control catalyst. Just 2 years ago, some researchers came to the opposite conclusion. Actually, by combining these metals, you reduce the activity of palladium, and you don't want to use these metals in tandem. Then just a couple months ago, we actually had another research group go back to the original conclusion that by combining these precious metals, you get the best possible emissions control catalyst. So I had a simple question maybe about a year ago, which was, first of all, why are there so many conflicting reports in the literature? And then finally, how do you build this ideal emissions control catalyst using sparing amounts of these precious noble metals? So when you're trying to understand why in the literature there are some conflicting results, you have to understand how most of these catalysts are being created. So traditionally, you'll take a platinum and a palladium salt, and you'll mix it with some inert supporting material, such as aluminum oxide. So the idea being that if you take platinum, which would be red, and palladium, which is blue, you combine and you get some purple alloy, intermetallic alloy, what have you. But the fact of the matter is that it's not as simple as that. You can create a host of different structures. So you can create a purple alloy. You can create phase-segregated materials with platinum-rich and palladium-rich regions, and a whole host of other different structures. And this has to do with the fact that these catalysts are made by mixing and then high-temperature thermal treatments to combine these metals. So first of all, it can be difficult to correlate activity with structure given a variety of different structures present. But second of all, you can understand why different researchers may come up with different results if they have different sorts of structures present. So our idea was pretty simple, which was to create a very uniform catalyst with a very single type of phase in order to be able to clearly correlate structure with property. So the example here being we have a single, all these darker spheres are the catalytically active nanoparticles for the methane combustion reaction, and all of them should be doing the reaction the exact same way. So the way that we create our catalyst is somewhat different than what you would do in the literature. Instead of mixing powders and heating them up, you create a type of ink. And then you drop this ink, which contains your active nanoparticles, onto your inert support. And then you can create a catalyst with these well-defined properties. By combining these traditional chemical approaches to these engineering problems, you can control the structure of your materials. So along with being able to control the size and the shape, we wanted to prove that each of these catalytically active nanoparticles on the left-hand third graph, each of those bright white spots represents a nanoparticle for this reaction. Each of them have the same amount of atoms of platinum and palladium. In other words, that each of these spheres is the exact same, like all the other ones on the catalyst. So you don't have multiple different phases with different activities. And then we created a library of these materials. By just tuning a single parameter, we kept size of these active nanoparticles the same, the shape, and we singularly tuned the composition of each of these active nanoparticles. With the question in mind, what is best for methane emissions control? Is it monometallic palladium, platinum, or is it one of these alloy compositions in between? So the next step in this study was to finally test these materials for the methane combustion reaction, or for methane emissions control. So you feed in methane and oxygen into your reactor, and you monitor how much of the methane is actually converted. So on this graph, you have on the x-axis temperature, and then on the y-axis, you have turnover frequency, which is a sense of how many times the reaction will occur on any given nanoparticle. And the first thing to observe is that although we have temperature on the x-axis, our y-axis is actually logarithmic. So as you move higher up on this y-axis, you have a logarithmically more active material. So you see you have one line way higher up than all the other materials, and that's the monometallic palladium catalyst. And then you have your 5 other materials, your pure platinum material as well as your platinum alloys, all clustered around the same region with comparable activities within a factor of 2 or 3. So the conclusion to take away for the methane combustion reaction is that incorporation of even very small amounts of platinum into your highly active palladium phase turns your palladium into platinum and shuts down the reactivity by a factor of thousands. So if you were to project this onto a line of turnover frequency, you have your bimetallic materials all clustered in one area with platinum, and then you have your highly active palladium material. So we wanted to test these materials for another reaction, perhaps more relevant, which is the combustion of hydrocarbons in the presence of steam. When you have your effluent coming from your gas engine, very often it's saturated with water, so we did the same methane combustion reaction in water. And the takeaway here is that all your materials all get shut down completely to the same activity. There's no real benefits to any particular composition in the temperatures that we were observing this reaction at. So we said activity is an important design parameter when designing expensive catalysts, the other one being stability. So how stable are these different materials? So we tested our 6 different catalysts. We tested the activity. We then aged them at 900 degrees, and then we tested the activity again. And here you can see as a function of composition the relative stability. So this black line going across the center, if you're below that line, it means that over this aging procedure, you lost some of your activity. So for example, your palladium and your platinum monometallic materials on either side lost 60 to 70% of their catalytic activity only after 1 hour. But we were really surprised to find this unique composition of palladium-rich bimetallic, which actually increased in activity over this very rigorous hydrothermal aging. And we were wondering, why can this material get better? This is not to be expected at all. And it was really helpful that we started off with these well-defined structures. So on the left-hand set of images, you have the original material, the top being the STEM image itself, and then the atomic mappings of platinum and palladium. uniformly distributed through each nanoparticle. And then on the right-hand side, you see something completely different. So no longer do you have very small nanoparticles, but you have quite large aggregates. And as people in heterogeneous catalysis know, you have reactions occurring over the surface, so you want to maximize the amount of surface area you have. So why would these aggregated materials be more active? Then if you do atomic mappings of these sintered materials, you notice the elements are no longer uniformly distributed. So you have all of your platinum signal move to one side of the nanoparticle, and you have your palladium signal move to the other side. So if you do some more careful analysis, you can see that you can actually distill out your palladium phase right back out, which we now know is truly what you want to have in your catalyst for this reaction. So you have these two combining mechanisms, loss of surface area, which is compensated for by the intrinsic promotion by this phase segregation behavior. And this kind of ties into why other literature reports see different things. If they're creating materials anything like what we saw after we aged them, it can be so incredibly difficult to understand what makes the best material, given the range of complexities and what you might see in your catalyst. So I hope I showed you that by creating even a small set of catalysts with very well-defined properties, it can be so valuable for correlating structure with activity, which we've seen in previous talks can be quite difficult. For this particular reaction, we see that the introduction of even small amounts of platinum to your very active palladium material completely shuts down activity by factors of thousands, essentially turning palladium, which is highly active, into platinum itself. And then by taking these well-defined starting phases and observing how they evolve through aging procedures, we can kind of reconcile it and bring it all together and understand why other researchers are going to be seeing a whole range of results. So I'd like to thank all the other researchers that helped with this project. We had lots of collaboration, both in theory with Frank Abel-Peterson, as well as characterization over in UC Irvine and Emmett Slack. And I'd be happy to answer any questions.
Thank you, very nice talk. So when you're looking at the phase segregation, would you expect the activity to decrease after an hour has transgressed and the phases separate? Do you expect it to then go down afterwards?
So you start off with a single phase, and as you cool your reactor, you have different phases separating, and that's when you get your promoted activity. As you heat the material back up, they remix, and you no longer have these multiple phases coexisting. So it's on the reactor cool down which you see the phase segregation and the increased activity as it precipitates out.